What if Earth lost gravity for 5 seconds? Not weakened gravity, not a strange magnetic effect, not the kind of weightlessness astronauts feel while orbiting Earth. Imagine that at one perfectly ordinary instant, the gravitational field produced by Earth simply vanishes everywhere, while Earth itself, its mass, its rotation, its atmosphere, its oceans, its buildings, its people, and every other law of physics remain exactly as they were. 5 seconds later, the field returns just as suddenly. At first, almost nothing looks dramatic. A woman is standing in a kitchen with one hand around a coffee mug. A child is halfway down a staircase. A passenger train is entering a station. A goalkeeper is leaning forward before a penalty kick. Far out in the Pacific, waves are moving toward a coastline. Deep below them, the ocean presses against the seafloor with thousands of tons of force over every large patch of rock. Deeper still, the mantle and core exist under pressures created over billions of years by the weight of the planet above them. Then gravity is gone. The woman does not shoot toward the ceiling. The coffee mug does not leap from her hand. The child does not instantly rise like a balloon. For the first fraction of a second, the strangest thing is not motion. It is the sudden absence of weight. The floor no longer has to push upward on the woman's feet to support her. The chair no longer has to support the person sitting in it. A hanging lamp no longer pulls on its cable with the same familiar load. An elevator car no longer weighs what its cables and counterweights were designed to balance. A suspension bridge loses much of the downward load that shaped the tension in its cables only an instant before. Across the planet, forces that have been quietly balanced for years, decades, centuries, or geological ages become unbalanced at once. And that is why 5 seconds would be enough. The danger is not that gravity is a switch holding loose objects to the floor and everything simply floats gently until it turns back on. The danger is that almost every large system on Earth has spent its entire existence adjusting itself to gravity. When gravity disappears, those systems do not become peaceful. They begin releasing the forces that gravity had been balancing. To make this impossible thought experiment coherent, we need one clear rule. Earth's own gravitational field vanishes for exactly 5 seconds. The sun still pulls on Earth. The moon still has its own gravity. Electromagnetism still holds atoms and molecules together. Chemical bonds do not disappear. Inertia remains. Earth's matter does not become massless. And when the 5 seconds are over, Earth's gravity returns to precisely its previous strength. No known physics can do this. General relativity does not treat gravity as a device that can be unplugged. Earth's mass and energy curve space-time, and there is no mechanism that lets a planet keep all its mass while its gravitational influence simply becomes zero and then returns on command. Even the idea of the change occurring everywhere around Earth at exactly the same instant creates problems with relativity and causality. So the mechanism is magic. The consequences are physics. And the first surprise is how different this would be from the International Space Station. Astronauts aboard the station are not floating because Earth's gravity has disappeared. At the station's altitude, Earth's gravitational pull is still strong. The station and everything inside it are continuously falling together around Earth. They move sideways so quickly that as they fall, Earth's curved surface keeps falling away beneath them. That continuous free fall creates the experience of weightlessness. Our 5 seconds are stranger. And before imagining anyone floating, we have to notice a detail that changes almost the entire story. The ground is not an inert stage. Earth itself has been compressed by its own gravity for billions of years. Inside a body in mechanical equilibrium, internal pressure and stress gradients help balance gravitational body force. The instant Earth's self-gravity vanishes, those pre-existing stresses do not vanish with it. For the first instant, the material of the planet is mechanically unbalanced. The outer Earth begins trying to move outward. This is the part that many versions of the thought experiment quietly freeze in place. They imagine a rigid Earth that somehow keeps its shape while people, cars, oceans, and air lose weight. That gentler version is useful as a classroom baseline, so we will calculate it. But it is not the literal version of Earth losing its own gravitational field. In the frozen ground version, suppose you are standing perfectly still relative to the floor. Removing a downward force does not create an upward force on your body. If there were no wind, vibration, structural motion, or other disturbance, you would initially continue almost along the inertial path you already had. Earth is rotating. At the equator, the surface is moving eastward at roughly 465 meters per second. If the planet were held magically rigid, its surface would keep curving around Earth's axis while a freely drifting person followed a straighter path through space. Over 5 seconds, that purely rotational separation would be about 42 centimeters at the equator, roughly half as much around 45 degrees latitude, and nearly zero at the geographic poles. That number is real mathematics. It is not, however, the predicted height of a person above the floor in our literal scenario. The floor is moving too. The stress field inside the crust and mantle had been helping support the planet against self-gravity. Remove gravity while those stresses are still present, and, in the first instant, material can experience outward acceleration of the same general order as the gravitational acceleration that had been balanced before. A naive estimate that pretended the old stress gradient stayed unchanged for all 5 seconds would imply motion on the scale of tens to more than 100 meters near the surface. That estimate is not a prediction. Rock is elastic. Stress changes launch waves. Different layers have different properties. Faults slip. The mantle, crust, oceans, atmosphere, and rotation all interact. Within 5 seconds, elastic information travels tens of kilometers through crustal rock, so the initial acceleration cannot simply remain unchanged everywhere. But the estimate reveals the scale of the mistake in imagining a perfectly still floor. In the literal scenario, local ground motion may dominate the 42-centimeter rotational effect. A person can briefly lose contact with a surface, then be struck or pushed by that same surface as the crust moves outward beneath a building. A house may carry its occupants with the moving ground. A bridge deck, tunnel, runway, and railway are all attached to a planet beginning to unload mechanically. Existing motion still matters. A person who had just jumped upward at 3 meters per second keeps that velocity instead of being slowed by ordinary gravity. A basketball player, gymnast, diver, construction worker, child on a trampoline, or someone already falling carries their existing velocity into the event. But there is no single universal answer to how many centimeters above the floor they will be after 5 seconds, because the floor itself is part of the experiment. A loose glass does not leap upward merely because its weight disappears. The counter beneath it, however, belongs to a building attached to a moving crust. Air begins moving. The building unloads. The counter can rise, tilt, vibrate, or shift beneath a glass that is trying to preserve its inertial motion. That difference will matter again and again. A pencil rolling slowly across a desk no longer has a reliable normal force creating friction. A toolbox in a moving truck can drift. A stack of boxes in a warehouse loses the compressive force holding the stack against the floor. A hospital bed still has straps and rails, but equipment resting beside a patient may not. A pot of boiling water no longer behaves like a pot of boiling water. Liquids are among the first familiar things to become unfamiliar. On Earth, gravity flattens the free surface of water and separates lighter gas above from denser liquid below. In apparent weightlessness, surface tension becomes far more important. Small amounts of water can gather into rounded blobs, cling to surfaces, and move according to wetting and inertia rather than simply settling to the lowest point. But an ocean is not a glass of water aboard a spacecraft. An ocean begins our 5 seconds with an enormous vertical pressure gradient inside it. That difference changes everything. Before we reach the oceans, consider a road. A car moving at highway speed depends on gravity even when the engine is doing all the obvious work. Tires produce steering and braking forces because they are pressed against the road. When weight disappears, the normal force between tire and pavement collapses. So does most of the available friction. For 5 seconds, steering wheels can turn while the tires do almost nothing useful. Brakes can clamp discs while the vehicle has little traction through which to transfer the force to the road. Driven wheels can spin. Vehicles that were already moving continue largely along their existing inertial trajectories. On a straight, level road, many would remain close to the pavement for the brief interval. On a curve, the story is worse. The road had been providing the lateral force required to bend the vehicle's path. Remove the normal load, and that force nearly vanishes. A car negotiating a bend wants to continue tangent to the curve. Banked roads become strange. Bridges become stranger. Motorcycles, which rely on a delicate relationship between speed, lean angle, tire forces, and gravity, become almost impossible to control for those few seconds. The drivers would not have time to understand what happened. Human reaction time is too slow for a clean response to an event this bizarre. By the time someone recognized that the steering had gone light, the countdown might already be halfway over. Trains are better constrained because steel wheels are guided by rails, but the normal loads that keep wheel flanges seated and suspensions compressed change abruptly. A high-speed train on a curve would experience an extraordinary transient as its weight vanished while its momentum continued. Cable cars, funiculars, cranes, amusement rides, and elevators would each respond according to how much of their normal tension and geometry depends on weight. An elevator is especially revealing. The car is usually balanced by cables, counterweights, motors, brakes, and control systems designed around predictable gravitational loads. When gravity disappears, the car and counterweight both lose weight, but their inertia remains. Cable tension changes. Any motion already underway continues. The control system may detect impossible sensor values. When gravity returns, the system is suddenly loaded again, potentially while the car, cables, and counterweight are no longer in exactly the positions or tensions they had 5 seconds earlier. Most elevators would not shoot through roofs or plummet down shafts. Safety systems are too complex for one universal outcome, but the brief unload and reload would create mechanical shocks in machines never designed for a world with zero gravitational load. The same thing happens at much larger scales. A suspension bridge is not simply a rigid object sitting on Earth. Its deck hangs from cables under tension. Towers carry compression. The entire structure is shaped by the constant weight of steel, concrete, vehicles, wind loads, and its own geometry. Remove the weight, and parts of the bridge elastically relax. 5 seconds is long enough for motion to begin. Then the load returns before the structure has settled. Tall buildings also change shape slightly under their own weight. Columns are compressed. Foundations carry load. Floors deflect. Pre-stressed concrete and tension members exist in carefully engineered balances. For 5 seconds, part of that balance vanishes. Buildings do not explode upward, but they can rebound, sway, and launch unsecured contents into unusual motion. When gravity comes back, everything is loaded again while some structures are still oscillating. The most dramatic engineered failures would probably not come from the absence itself. They would come from the return. And then there is the air. At sea level, you live beneath an atmosphere whose pressure is created largely by the weight of the air above. In a calm atmosphere, the downward pull of gravity is approximately balanced by an upward pressure gradient force. Pressure decreases with altitude because every layer supports less air above it than the layer below. For a parcel of air sitting quietly before our event, those forces are close to balance. Gravity pulls downward. The pressure gradient pushes upward. Then one of them disappears. The pressure field does not instantly know how to become a zero-gravity pressure field. For an instant, the atmosphere still has the same vertical pressure gradient it had a moment earlier, but the downward gravitational force is gone. Now the gradient is unbalanced. In an inertial frame, atmospheric parcels initially acquire an outward acceleration because the pressure gradient force that had balanced gravity is still present. But the word outward needs care. The surface beneath the atmosphere is also beginning to move outward as the solid Earth unloads. In the simplest local hydrostatic picture, both air and the material beneath it were responding to nearly the same gravitational field before the event. Removing that field, therefore, gives large parts of the atmosphere and the ground a partly shared outward impulse. The dangerous motion is not simply air racing upward above a stationary planet. It is the difference between how compressible gas, elastic rock, mountains, buildings, and the ocean respond to the same sudden loss of gravity. The atmosphere is highly compressible, so those responses diverge quickly. Pressure waves move through it. Density changes. Existing winds and temperature structures matter. Terrain moves differently from the gas above it. Open air, sealed rooms, valleys, storm systems, and high mountains all develop different local motions. 5 seconds is not negligible for air. Sound travels through the lower atmosphere hundreds of meters each second. In 5 seconds, pressure information can move more than a kilometer. The atmosphere, therefore, begins a rapid global adjustment, but not as a shell cleanly peeling away from a fixed surface. It moves as one layer of a planet whose other layers are moving too. At mountain summits, in deep valleys, over oceans, inside storms, and across the poles, the response would differ. Winds already moving would keep their horizontal momentum. Pressure systems would not vanish. Warm and cold air masses would still differ in density and temperature. Yet the vertical balance underlying the entire atmosphere would suddenly be removed. Barometers would record something no meteorologist had ever seen. Weather balloons would enter a new kind of motion. Cloud droplets would no longer settle in the usual way. Raindrops already falling would stop accelerating downward and continue with the velocity they had at the instant gravity disappeared, slowed by air drag that was itself changing. Snowflakes would drift according to inertia and turbulent air. Hailstones would suddenly become much easier for rising air to carry. Birds would have a confusing 5 seconds. Flight is already a balance of lift, weight, thrust, and drag. Remove weight, and a bird producing the same lift as a moment earlier suddenly has a large, unbalanced upward aerodynamic force. But the air through which it flies is itself beginning to expand outward. Some birds would fold their wings or tumble. Others would gain altitude abruptly. Many would not understand the new relationship quickly enough to control it before gravity returned. Aircraft faced the same problem at higher speed. An airplane in level flight begins with wings generating lift roughly equal to its weight. When Earth's gravitational field disappears, that aerodynamic force does not vanish instantaneously. If the surrounding air remained an ordinary stationary atmosphere, the airplane would be strongly overlifted. But the surrounding air is not stationary. It is participating in the same global pressure imbalance. The aircraft, the air mass around it, and the ground far below no longer share their usual accelerations. So there is no single clean upward acceleration that applies to every airplane. For the first moments, lift, thrust, drag, aircraft inertia, atmospheric vertical motion, and control system responses all compete. Autopilots are designed to interpret acceleration, attitude, pressure altitude, and airspeed inside a one-gravity atmosphere. None are designed for the atmosphere itself to enter a planet-wide non-hydrostatic transient. Passengers would lose the familiar seat load. Loose objects could drift. Drinks would break into moving blobs and droplets. Standing crew could lose contact with the floor. 5 seconds later, gravity returns while both aircraft and atmosphere already carry motions that did not exist before the event. Most high-altitude aircraft would still be in the sky. 5 seconds is far too short for them to fly away from Earth. But the global atmospheric pulse that follows could make the minutes after the event far more dangerous than the weightless interval itself. And now we reach the ocean. This is where one more intuition has to be corrected. Every cubic meter of seawater begins the event inside a vertical pressure field created by gravity. Deeper water is at higher pressure because it supports the weight of water above it. In a local hydrostatic description, the upward pressure gradient force and the downward gravitational body force nearly cancel. Remove gravity and the pressure gradient force remains for the first instant. So the water acquires outward acceleration. But the seafloor is not fixed. The rock beneath the ocean was also in a stress state that helped balance self-gravity. It begins moving outward too. In the simplest imaginary case of a perfectly uniform, non-rotating planet made of layers that all responded identically, much of the water and the rock below it could initially accelerate outward together. The ocean would not need to leap hundreds of meters above a motionless basin. Real Earth is nothing like that simple model. Water is far more compressible and mobile than crustal rock. The strength of gravity changes with depth and position. The seafloor is irregular. Continents interrupt basins. Rock supports shear stress while liquid water does not. Temperature and salinity change density. Coastlines create boundaries. Existing waves and currents already carry momentum, and the free surface has no solid layer above it moving in the same way. Those differences generate relative motion. The speed of sound in seawater is roughly 1,500 meters per second. Across an average ocean depth of about 3.7 kilometers, acoustic information can cross the water column in only a few seconds. 5 seconds is therefore enough for pressure readjustment to begin across much of the vertical ocean in many places. But the relevant question is no longer, how high does the ocean rise above a fixed Earth? The question is, how differently do ocean, crust, and atmosphere move while the entire planet is being kicked outward? That is a much harder problem. Ordinary surface gravity waves also lose their main restoring force during the interval. Rivers no longer have the same gravitational tendency to run downhill. Waterfalls carry their existing motion but no longer accelerate downward. Reservoir hydrostatic loads change. Pipes and water towers lose elevation-created pressure. Hydroelectric turbines enter a flow state no control system was designed to see. Then the 5 seconds end. And here is another important correction. Gravity returning does not make everything instantly reverse direction. Velocity does not disappear because a force has returned. At the end of the 5 seconds, rock, water, and air can all possess outward velocities. Restored gravity again pulls inward, but the old pressure and stress fields have not vanished either. For a short time, they may still oppose much of that restored gravity, just as they did before the event. So the planet can keep expanding after gravity is back. The same principle is familiar from any oscillator. Restoring force may point toward equilibrium while the moving object continues past it because it already has momentum. Earth has real free oscillation modes. Its fundamental radial or breathing mode has a period of roughly 20 minutes. That does not tell us the amplitude produced by our impossible 5-second event, but it tells us something crucial about timescale. 5 seconds is a short kick compared with the time a whole planet takes to complete a radial oscillation. The event ends while Earth is still being launched into motion. A naive local calculation that left the old pressure or stress gradient unchanged for all 5 seconds could give surface material an outward velocity of several tens of meters per second. That is not a reliable global prediction because stress waves and material properties matter. But even a much smaller fraction of that velocity would be enormous on a planetary scale. When self-gravity returns, the solid Earth begins a global breathing response. The crust, mantle, and core do not simply snap back to their original positions. They continue moving, overshoot, exchange energy among elastic and gravitational modes, and gradually damp. The ocean rides on a seafloor participating in that motion while also supporting its own acoustic and gravity wave responses that can generate basin oscillations, pressure waves, coastal surges, seiches, and strong local flooding. But it is misleading to picture one universal shell of ocean thrown upward and then dropped back onto a stationary Earth. The atmosphere behaves similarly in principle and differently in detail. It too carries outward momentum after gravity returns. Because it is compressible and thin compared with the solid planet, its pressure waves and density changes occur on different timescales. The result can include strong vertical motion, pressure jumps, turbulence, and winds. But again, the motion is relative to a surface that is itself moving. So which is worse, ocean, atmosphere, or solid Earth? The most defensible answer is that the solid Earth's global radial kick sets the stage, while atmosphere and ocean add their own differential responses on top of it. And the exact severity is not something a one-sentence impossible premise can calculate honestly. What we can say with confidence is more interesting than a fake tsunami height. Gravity had been part of the equilibrium of every major layer of the planet. Removing it gives the whole system momentum. Returning it does not erase that momentum. That is the real physics hiding inside the 5-second question. Now imagine the event second by second. At 0 seconds, every gravimeter on Earth drops toward a reading that should be impossible. Sensitive instruments designed to measure tiny variations in local gravity encounter a change many orders of magnitude larger than anything they were built to record. Spring gravimeters unload. Pendulums cease behaving as pendulums. Seismometers experience motions from their own suspensions before the planet itself has even begun its larger elastic response. Atomic clocks keep ticking. Light keeps moving. Radio continues. Electricity still flows through wires. The event is not a universal pause in physics. It is the removal of one relationship that had quietly shaped almost everything else. At a breakfast table, a spoon ceases pressing on the tablecloth. It may remain almost exactly where it was for the first instant. Then the table vibrates, air begins to move, and a tiny sideways push sends it drifting. At a swimming pool, swimmers no longer need buoyancy to oppose weight. Buoyancy itself changes because buoyant force in an ordinary fluid comes from a pressure gradient created by gravity. The water is beginning its own pressure-driven response. A swimmer does not simply become an astronaut inside a calm pool. The entire fluid environment is reorganizing around them. At a hospital, intravenous drips that depend partly on gravity change flow. Drainage systems change. Equipment on articulated arms unloads. Patients restrained by bedding remain more controlled than loose objects, but staff standing in corridors lose traction. At a construction site, a crane's suspended load stops pulling downward on the cable. The cable tension drops sharply. The boom structure rebounds. The load keeps whatever horizontal motion it already had from wind or crane movement. When gravity returns, slack cable can snap taut under a suddenly restored load. At a shipping port, container stacks lose weight. Twist locks still connect many containers, but friction between unsecured surfaces becomes nearly useless. Gantry cranes unload. Ships cease displacing water in the ordinary gravitational sense because buoyancy depends on the same hydrostatic pressure field now breaking apart. A ship does not instantly sink or fly. Its mass remains. Its hull remains. Water remains around it. But the pressure distribution that supported the hull changes, while the ocean itself begins accelerating. 5 seconds later, the ship may meet returning gravity inside water that is no longer in anything like its original state. At an oil refinery, vertical separation processes that rely on gravity are briefly disrupted. Storage tanks lose hydrostatic head. Floating roofs and liquid levels change. Pumps continue running until sensors or power systems intervene. The 5-second event is too short for most automated systems to understand, yet long enough to create fluid transients that may cause problems after gravity returns. At a mine, loose rock no longer presses downward, but tunnels are not suddenly safe. Excavations exist in stress fields partly produced by the weight of overlying rock. Rapid unloading and reloading can fracture material. Dust hangs. Machinery loses traction. Miners working at depth are surrounded by rock that is joining Earth's larger elastic response. At a ski resort, someone halfway through a jump continues upward far longer than expected. At a football stadium, a kickball stops following its normal parabola. Its path becomes almost a straight line modified by air drag and the motion of the atmosphere. Players lose traction at the same moment. A goalkeeper who had launched sideways continues drifting rather than falling. At a baseball game, a high-fly ball no longer curves downward. For 5 seconds, it continues outward with its existing velocity. If it was moving upward when gravity vanished, it keeps climbing. When gravity returns, the ball may be tens of meters from where anyone expected it. At a diving competition, the consequences can be severe. A diver already moving downward continues downward instead of accelerating, perhaps reaching the water differently. A diver who has just pushed upward from a board may travel far above the pool before gravity returns. At a mountain cliff, loose stones do not immediately leap away, but the normal force holding them against surfaces disappears. Friction depends on normal force. A rock resting precariously on a slope can begin sliding or drifting according to tiny existing forces. Then the ground itself shakes when the planet reloads. In the rigid Earth classroom version, latitude produces a clean pattern. The rotational separation is largest at the equator and approaches zero at the poles. In the literal version, that elegant pattern is buried inside a much larger signal. The crust itself is moving. Buildings are riding that motion. Air is moving. Local geology differs. Elastic waves arrive from surrounding regions. A polar observer avoids the rotational contribution, but not the mechanical unloading of the planet beneath their feet. Scientists could still recover Earth's rotation from the data later by comparing inertial trajectories with precise ground motion. But ordinary videos would not show a simple rule in which equatorial people float 40 centimeters while polar people stay on the floor. The planet has become part of the trajectory, and this corrects two common intuitions at once. Earth's spin does not create gravity, and Earth is not merely a platform on which gravity acts. Its own gravity is part of what gives the planet its present stressed shape. By the end of the first second, most people have not yet understood what is happening. Those standing indoors feel their feet leave reliable contact with the floor. Those sitting feel the seat stop supporting them. Anyone wearing a seat belt, harness, climbing rope, or snug restraint has an immediate advantage. Loose hair drifts. Clothing stops hanging downward. Dust lifts from surfaces as air begins moving. Liquids slosh in ways that look wrong. Dogs scramble for traction that is no longer there. Cats push against furniture and drift more than they intended. Horses in fields lose the familiar relationship between hoof and ground. Large animals, with great inertia and no understanding of the event, can injure themselves against fences or structures. By the second, the atmosphere's vertical adjustment is underway. Pressure sensors are recording rapid change. Aircraft computers are issuing alerts that make no sense within their normal operating assumptions. Cars on curves are departing from expected paths. Boats and ships are entering disturbed water. By the second, pressure disturbances in shallower seas have had time to cross substantial portions of the water column. In the deep ocean, acoustic information is still propagating. Water and seafloor are both moving outward, but not identically, and those differences are beginning to create pressure and relative motion signals. Deep inside Earth, rock is accelerating according to altered stress balance. Elastic waves launched by the sudden unloading are traveling through the crust and mantle, while the bulk radial motion continues. By the second, the event feels long. 5 seconds sounds tiny when measured by a clock. It is enormous when the expected event duration is 0. A person inside a bedroom may have time to see the mattress rebound, loose objects drift, and then the room itself begin moving with the building and crust beneath it. A pilot has time to grip the controls. A driver has time to press a brake pedal and discover that the car is barely responding. A climber has time to feel a rope go slack. A surgeon has time to watch a droplet move away from where droplets are supposed to go. No one has time to create a plan. Then comes the second. Gravity returns, and the quietest part of the disaster ends. When gravity returns, unsupported objects once again feel an inward gravitational acceleration. But that does not mean they immediately fall toward a floor. The floor may still be moving outward. So may the building. So may the local ground. A person and a room can therefore continue separating for a while even after gravity is back, or the moving room can overtake the person from below. The relative motion depends on velocities accumulated during the 5-second interruption. For millions of people, those relative velocities are enough to create injury. There is no single global fall height. Some people remain close to a nearby surface. Others were carried or struck by moving structures. Some already had large velocities. Furniture, tools, dishes, phones, books, toys, lamps, boxes, and fragments of material all enter the restored gravity phase with their own trajectories, while the structures around them are part of Earth's continuing oscillation. The danger is therefore not simply falling after 5 seconds of floating. It is collision inside a moving reference frame. Some are horizontal. Some are upside down. Some are elderly, injured, asleep, holding infants, carrying glass, working beside machinery, or floating beneath hard ceilings and metal shelves. A 5-second event happening to billions of people creates billions of different geometries. A person who was sleeping may remain close to the mattress, yet still be struck by it or separated from it as the room moves. Someone beside a staircase may drift into open space while the stair structure itself shifts. A worker on a ladder may no longer be aligned with the ladder when gravity returns. A mechanic beneath raised equipment may face machinery that moved during the unload. A warehouse worker may be beneath objects that were stacked safely only while normal forces and restraints behaved normally. In homes, the sound arrives almost at once. Objects hitting floors, glass breaking, furniture slamming back into contact, people shouting, alarms beginning, then larger sounds begin joining them. A jumper who carried 3 meters per second of upward velocity for the full 5 seconds can be roughly 15 meters higher than expected. When gravity returns, the fall takes less than 2 seconds to become dangerous. A faster upward launch can be worse. This makes the event grotesquely selective. Most people were not jumping at that exact instant. But across 8 billion lives, someone was. Thousands of athletes were running, leaping, diving, climbing, falling, or working at height. Millions were in moving vehicles. Tens of thousands were aboard aircraft. People were riding bicycles, motorcycles, elevators, amusement rides, cable cars, and escalators. Construction cranes were carrying loads. Shipping cranes were moving containers. Surgeons were operating. Factories were running at full speed. Gravity returns to all of them simultaneously. For the first few seconds afterward, accidents multiply before the global fluid and geological effects fully arrive. Cars that had lost traction hit the road again, often while slightly misaligned. A vehicle that drifted only a few centimeters can land hard enough to damage suspension or lose control at highway speed. Cars that entered curves during the event may leave lanes. Motorcycles can come down at the wrong lean angle. Trucks with shifted cargo become unstable. A train whose wheels unloaded against a rail can experience impact when wheel loads return. Some derail. Most do not. The difference depends on speed, track geometry, suspension, and where the train was within a curve or switch at the exact moment. Airplanes suddenly regain weight. An aircraft that climbed during the 5-second interval may now have upward velocity as gravity returns. Pilots and autopilots begin correcting. Wings still produce lift. Passengers come down against seats, ceilings, armrests, or belts depending on cabin motion. The event itself ends, but the atmosphere around the aircraft has not returned to its old state. That atmosphere is now moving. During the 5 seconds, its hydrostatic balance was disturbed and the ground beneath it was moving as well. Once gravity returns, the air does not simply reverse and collapse. It already has momentum. Restored gravity begins contributing an inward force again, while pressure gradients, density changes, terrain motion, and existing winds continue acting. Some air keeps moving outward for a time. Other regions compress sooner. Pressure waves travel through the gas and reflect from the moving lower boundary. The atmosphere therefore overshoots in a complicated way. There would likely be strong vertical and horizontal motions, pressure jumps, turbulence, and winds generated by the coupled readjustment of atmosphere and planet. The exact pattern would be extremely complicated because the atmosphere was not initially uniform. It already contained storms, jet streams, temperature inversions, mountain waves, hurricanes, sea breezes, and countless local circulations. The 5-second removal of gravity adds a global vertical disturbance to all of them at once. Imagine striking every pipe in a cathedral organ at the same instant, except each pipe was already playing a different note. That is closer to the atmosphere after gravity returns. Windows flex under pressure changes. Doors slam. Trees bend in sudden gusts. Aircraft encounter severe turbulence. Dust and debris lifted during the weightless interval become projectiles when both wind and gravity act again. Weather stations around the world begin generating data so strange that automated quality control systems may flag it as sensor failure. But the sensors are not failing. The atmosphere is. For a short time, the familiar approximation of hydrostatic balance no longer describes it. Then the coupled ocean response begins reaching coastlines. Not because an entire ocean shell was dropped back onto Earth, but because water and basin move differently during a global radial disturbance. Ocean basins need time to communicate those differences horizontally. Waves must travel. Coastlines focus or disperse energy. Some regions may first experience modest changes, followed minutes or hours later by larger surges generated by basin geometry, seafloor motion, landslides, or resonant oscillation. The response would contain many scales at once. Acoustic pressure waves through the water column. Long-period basin oscillations. Local waves generated by differential seafloor motion. Currents altered by the temporary loss of the gravitational restoring force. Coastal surges amplified by harbor or shelf geometry. Harbors can resonate. Rivers near the coast can carry surges inland. Low-lying deltas may flood. But there is no scientifically defensible universal tsunami height, and no reason every coast must experience the same sequence. Warning networks would record extraordinary pressure and sea level signals, while models built for ordinary earthquakes struggled to interpret a planet-wide source. And coastal communities may already be dealing with power failures, damaged roads, vehicle crashes, atmospheric turbulence, landslides, and the solid Earth's continuing radial and seismic oscillations. The planet's elastic response does not look like one conventional earthquake with one epicenter. There is no single point from which all shaking spreads. The disturbance was distributed through the planet. Seismometers begin recording global oscillations. Some faults experience abrupt changes in stress as the gravitational load vanishes and returns. A fault that was already close to slipping may fail. A mountainside held barely stable by friction can collapse after normal stress changes, shaking, or heavy rain already present. Submarine landslides can add more local tsunami energy to oceans that are already disturbed. Volcanoes do not all erupt. That would be another seductive but false simplification. Magma systems vary enormously. 5 seconds is short. Most volcanoes would not suddenly receive enough new energy to erupt. But magma chambers, hydrothermal systems, fractures, and volcanic slopes are pressure sensitive. Some systems already near instability could respond to the unusual stress transient. The event might trigger eruptions that would otherwise have occurred later. Others would show only changes in seismicity, gas flow, or groundwater. The most dangerous hours are therefore not one clean catastrophe. They are a pileup. Transportation accidents, structural failures, atmospheric shocks, ocean surges, earthquakes and landslides, industrial incidents, fires, power outages, communication congestion, emergency services trying to determine whether the impossible event is over. And somewhere above all of this, hundreds of kilometers into space, satellites have experienced their own 5 seconds. Here the physics is cleaner. A satellite in low Earth orbit is continuously falling around Earth. Earth's gravity bends its trajectory downward so that it follows the planet's curvature. Remove Earth's gravitational pull for 5 seconds, and the satellite stops curving along its normal orbit. It travels almost along the tangent line it had at the start of the interval. At roughly 400 kilometers altitude, where many crewed and uncrewed spacecraft operate, Earth's gravitational acceleration is still close to 9 meters per second squared. If that inward acceleration disappears for 5 seconds, the satellite ends up roughly 100 meters away from the position it would have occupied along its normal curved path. Using a simple short time estimate, 100 meters sounds enormous compared with orbital navigation precision. It is tiny compared with the size of an orbit. When gravity returns, the satellite is not automatically destroyed. Its position and velocity now correspond to a slightly different orbit. Some spacecraft would need corrections. Conjunction predictions would have to be recalculated. Formation flying missions could be disrupted. Satellites passing close to one another might face new collision risks because every orbit has been perturbed according to altitude and direction. But the majority of satellites would remain bound to Earth. At GPS altitude, the missing gravitational curvature over 5 seconds produces a much smaller displacement, on the order of several meters. At geostationary altitude, only a few meters. The effect decreases with distance because Earth's gravitational field is weaker there. The Moon is farther still. At the Moon's average distance, Earth's gravitational acceleration is only a few thousandths of a meter per second squared. 5 seconds without Earth's pull would let the Moon continue along a slightly straighter path than normal, shifting it from its expected trajectory by only a few centimeters during the interval. The Moon does not fly away. Its orbital speed is about 1 kilometer per second. The absence is simply too short to release it from Earth. When gravity returns, the lunar orbit is changed by a tiny amount. measurable with precise instruments, but not remotely enough to send the moon wandering through the solar system. This distinction matters because it exposes another common mistake in the thought experiment. If Earth truly loses its gravitational field, the effect cannot logically stop at the atmosphere. It must affect satellites and the moon too. The source gravity disappears everywhere around Earth. Our magic rule cannot say loose objects float while orbital objects somehow continue feeling the same Earth unless we are inventing two different kinds of gravity. For 5 seconds, the moon and satellites also feel the absence. They simply have too much distance and too much orbital inertia for 5 seconds to do much. Earth's orbit around the sun is different. Earth orbits because the sun pulls on Earth, not because Earth pulls on itself. We have not switched off the sun's gravity. The planet therefore continues moving around the sun almost exactly as before. Strictly, if Earth's gravitational field vanished, Earth would also stop pulling on the sun for 5 seconds, violating the mutual nature of gravity in a physically nonsensical way. That is one more reminder that our mechanism cannot exist. But if we accept the magical rule as an imposed change to Earth's field, the planet's solar trajectory during 5 seconds is essentially unchanged. The same is true of Earth's rotation. Gravity does not cause the planet to spin. Angular momentum carries rotation onward. 5 seconds without self-gravity can change Earth's shape and internal motion slightly, which could alter rotation by tiny amounts afterward, but the planet does not stop turning. This continuing rotation is why latitude mattered for people on the surface. It is also why the sky after the event looks normal. The sun has not jumped. The stars have not moved. The moon is still where it should be to the naked eye. For many people standing inland, away from major structural and industrial hazards, the first visual impression after gravity returns may be almost absurdly ordinary. The horizon is where it was. The sky is blue. Trees are still standing. Then alarms, sirens, broken glass, wind, shaking, and news begin revealing the scale. One of the first questions scientists would ask is whether Earth has lost any significant fraction of its atmosphere. The answer is almost certainly no. Atmospheric molecules do not need only the absence of gravity. They need enough outward speed and enough time to escape far enough that the returning gravitational field cannot recapture them. Earth's escape speed from the surface is about 11.2 kilometers per second. Normal molecules in the lower atmosphere move rapidly on a microscopic scale, but their thermal speeds are generally far below escape speed, and collisions constantly change their directions. The pressure-driven expansion during 5 seconds might give bulk air velocities of tens of meters per second in some regions, perhaps more in localized flows depending on the detailed response, but that is still tiny compared with 11,000 meters per second. When gravity returns, almost all of the atmosphere is still nearby and still gravitationally bound. Even air that moved hundreds of meters upward would simply become part of the collapsing and oscillating atmospheric response. Earth does not become an airless world. Oxygen does not vanish into space. People are not left gasping because the atmosphere was lost in 5 seconds. The air itself, however, may injure people through violent motion and pressure changes. The same logic applies to oceans. Water does not escape Earth in bulk. Even a parcel moving upward at tens of meters per second is nowhere near escape speed. The water remains gravitationally recoverable when the field returns. The problem is not losing the ocean. The problem is dropping it back into a gravitational world while it is moving. That difference turns a seemingly apocalyptic statement into a more precise one. Earth keeps its atmosphere. Earth keeps its oceans. Human civilization may still have an awful day. How awful depends greatly on where you are. Consider an inland town near the geographic poles. The rotational contribution is tiny and there is no direct coastal surge. That helps, but the ground is not protected by latitude. The crust beneath the town is part of the same global mechanical unloading and reloading. A low wooden house may tolerate distortion better than a brittle high-rise, or it may be damaged by foundation motion, pressure transients, and later seismic waves. People there avoid one source of relative motion. They do not avoid the planet's own response. Some communities could still fare far better than low coastal megacities, but the difference would depend more on geology, construction, terrain, and secondary hazards than on the simple 42-centimeter rotation calculation. Now consider a dense equatorial coastal city built on low ground. Rotational separation is larger. Traffic is heavy. High-rises sway through unloading and reloading. Port infrastructure experiences fluid and structural transients. The ocean is nearby. The atmosphere is warm and energetic. Underground transit may flood after surges. Electrical substations lie close to sea level. Emergency routes can be blocked by crashes and debris. The same 5 seconds produce a dramatically different disaster. Now move to an aircraft over open ocean. The airplane is unlikely to leave Earth during 5 seconds, but survival depends on its altitude, attitude, structural response, and the atmospheric motion around it. The cabin may remain intact while the larger danger develops after the interval. Severe turbulence, navigation errors, damaged airports, and an atmosphere still adjusting above a moving planet. Now move to a submarine. A submerged submarine begins inside a pressure field determined by depth. It is designed to balance buoyancy, ballast, and weight. When gravity disappears, weight and ordinary buoyancy both change because the hydrostatic pressure gradient is changing. The surrounding ocean is moving. Ballast systems are suddenly operating in a world for which their control logic has no model. 5 seconds later, gravity returns while the submarine and water around it may have acquired unexpected vertical velocities. Crews would feel violent transient loads. Some vessels survive. Some may collide with seabed or suffer structural problems if local pressure changes are severe. Now imagine a deep-sea organism. A fish living thousands of meters below the surface is adapted not just to darkness, but to enormous ambient pressure. The 5-second loss of gravity does not make deep ocean pressure instantly vanish. Pressure changes propagate through water at acoustic speed. In shallow water, the adjustment can reach through the whole column quickly. In the deepest trenches, 5 seconds may not be enough for a complete pressure readjustment from seafloor to surface. This means different depths experience different histories over the same 5 seconds. Some organisms encounter rapid pressure changes. Some encounter strong water motion. Many survive because the duration is brief and their bodies are largely water, reducing damaging pressure differentials across tissues. Gas-filled spaces are more vulnerable. Marine mammals near the surface may be thrown by water motion. Coral reefs can be damaged by surge and debris. Coastal ecosystems may be buried, exposed, or inundated. Terrestrial ecosystems fare differently. A forest does not float away. Trees are rooted. Their wood and roots remain chemically bonded. Gravity unloading reduces forces on trunks and branches briefly, while wind and atmospheric motion change. Some trees rebound elastically. Loose branches and fruit drift. Birds and insects lose ordinary flight balance. When gravity returns, forests experience wind, falling debris, and seismic shaking. Roots keep most trees connected to soil, but landslides on steep terrain can transform whole valleys afterward. Animals on open plains are not simply lifted a few centimeters and returned. They are standing on terrain that may itself move, while air, water, trees, fences, and slopes respond around them. Running animals carry existing velocity. Burrowing animals are constrained by tunnels, which can protect them from free drift but expose them to deformation and collapse. Ocean and coastal wildlife faces the additional violence of the fluid response. What happens to the biosphere as a whole is much harder to rank than the rigid ground version suggests. There is no years-long impact winter built into the premise, no deliberate removal of sunlight, and gravity returns after 5 seconds. Those facts make this very different from Chicxulub. But once the solid Earth's response is included honestly, it would be too confident to promise that the event is merely a severe disaster rather than a biological catastrophe. The scale of global ground motion, ocean disturbance, landslides, fires, and secondary failures depends on the exact impossible mechanism and on a full dynamic Earth model we do not possess for such a scenario. Earth would still have sunlight, atmosphere, oceans, chemistry, and gravity afterward. Whether ecosystems and human civilization emerge merely damaged or globally devastated is one of the quantities our one-sentence premise cannot determine honestly. The first hour after gravity returns would be defined by uncertainty. No government has a protocol labeled global gravity failure. Emergency systems are built around hazards humans have observed or can plausibly model: earthquakes, tsunamis, storms, wildfires, cyber attacks, industrial accidents, war. Our event combines pieces of several categories while violating the assumptions behind all of them. Emergency managers receive contradictory reports. Coastal flooding in regions that were not near an earthquake epicenter. Ground shaking across enormous areas. Aircraft declaring emergencies after impossible accelerometer readings. Satellite operators reporting simultaneous orbit errors. Hospitals describing patients injured by falls from inside closed rooms. Meteorological stations recording pressure disturbances that appear almost global. Seismological networks detecting a signal with no single source. The first human instinct would be to search for a cause. Weapon, solar event, cyber attack, unknown astronomical phenomenon, sensor failure. No explanation survives contact with all the evidence. A cyber attack cannot make loose objects weightless. A solar storm cannot switch off Earth's gravitational field. A nuclear weapon cannot perturb the moon's orbit by the same impossible 5-second signature measured by lunar ranging and spacecraft tracking. Within minutes, physicists around the world would be looking at data that cannot fit inside known theory. But the emergency comes before the Nobel Prizes. Power grids would be under enormous strain. Gravity itself does not keep electricity moving through wires, so generating stations do not all shut down during the 5-second interval. But the infrastructure around them experiences mechanical shocks, fluid transients, seismic motion, wind, transportation accidents, and sometimes flooding. Hydroelectric plants are hit especially strangely because their energy source depends directly on gravity pulling elevated water downhill. For 5 seconds, the gravitational head that normally drives turbines disappears. Water already moving through penstocks keeps moving through inertia and pressure, but the entire flow condition changes. Turbine controls see abrupt changes in torque and flow. When gravity returns, head returns while water columns may be oscillating. Some plants trip offline. Thermal power plants have pumps, condensers, tanks, cooling systems, and rotating machinery that are less directly dependent on gravitational head, but still sensitive to fluid levels, lubrication, structural loads, and grid stability. Nuclear reactors have another important distinction. Gravity disappearing does not stop nuclear fission by itself. Reactor protection systems respond to abnormal operating conditions according to design. If severe vibration, power instability, flow anomalies, or other trip signals occur, many reactors would shut down automatically. But shutdown does not remove decay heat. Cooling remains essential after fission is reduced. The gravity event is brief. The challenge afterward is ordinary engineering made harder by extraordinary damage. If cooling systems have power and water, shutdown reactors can be stabilized. If coastal flooding, grid failure, pipe damage, or seismic effects disable multiple layers of support, some sites could face serious emergencies. The event does not guarantee a worldwide nuclear catastrophe. It does create the kind of simultaneous infrastructure stress that safety systems are designed to avoid. Electric grids themselves depend on balance. Generation and demand must match closely. When regions abruptly lose power plants, substations, transmission lines, and loads at the same time, protective systems isolate faults. Large, interconnected grids can fragment into islands. Some islands remain stable. Others collapse. Blackouts spread not because gravity switched electricity off, but because gravity damaged enough things at once that the network can no longer maintain its carefully coordinated state. Restarting a large grid after widespread shutdown is not as simple as turning on one giant switch. Certain generating units must be capable of starting without outside power. Operators then rebuild islands, synchronize them, restore transmission paths, and add load carefully. Human coordination matters enormously. The 5 seconds are over. The recovery could take days, weeks, or longer in the hardest hit regions. Water systems also reveal gravity's hidden role. Many municipal water networks use elevated reservoirs and water towers to create pressure. During the gravity-free interval, that hydrostatic head vanishes. Pumps keep spinning if powered, but pressure patterns become abnormal. After gravity returns, liquid columns may still carry velocities acquired during the transient, so pressure oscillations and water hammer can damage pipes and valves. Sewer systems that rely on downhill flow stop behaving normally for 5 seconds, then restart into networks that may have shifted or cracked during shaking. Storm drains may already be overwhelmed by coastal surge or broken mains. Cities can lose clean water even when the reservoirs themselves remain full. That is one of the deeper lessons of the event. Gravity is not merely the force that keeps people from floating. It is built into the architecture of civilization. Water towers assume it. Sewers assume it. Dams assume it. Elevators assume it. Scales assume it. Drainage assumes it. Fuel systems assume it. Many industrial separators assume it. Every engineer designs inside a universe where downward is reliable. Then there are the dams. For 5 seconds, water stops exerting the usual gravity created hydrostatic load against dam walls. A concrete arch dam briefly unloads. An embankment dam loses part of the pressure conditions in its reservoir and within its own saturated material. After gravity returns, the reservoir, dam, and foundation may still be moving relative to one another, so the hydrostatic state reestablishes through a dynamic transient rather than instantaneously. Most well-built dams would probably remain standing through 5 seconds of unloading by itself. The greater danger is the combined transient, water motion, seismic shaking, landslides into reservoirs, damaged spillways, and power loss. A single large dam failure can devastate a valley. Our event gives thousands of dams unusual loads at once. The same multiplicity makes casualty estimates almost meaningless without assumptions. If someone asks how many people would die, the honest answer is not a neat number. It depends on the ocean response model. It depends on the solid Earth's elastic response. It depends on time of day. It depends on weather. It depends on how many secondary industrial accidents occur. It depends on which faults are close to failure. It depends on whether the 5 seconds happen during rush hour, during a quiet night, during a major hurricane, during winter, or during a period of calm seas. The direct floating and falling injuries could be relatively small compared with a global population. The secondary disasters could be enormous. This is why the scenario becomes more interesting when we stop asking, would everyone die? And ask instead, what did gravity actually do for us before it disappeared? The answer keeps growing. It maintained the atmosphere's vertical structure. It kept oceans pressed into basins. It helped compress the planet into its present mechanical state. It bent satellite trajectories into orbits. It gave rivers a downhill direction. It gave buildings predictable permanent loads. It created buoyancy. It gave friction a normal force. It gave pendulums a restoring force. It gave your inner ear a stable reference for up and down. The human body is accustomed to gravity so completely that even 5 seconds would be neurologically strange. Your vestibular system contains organs that sense linear acceleration and head orientation relative to gravity. Tiny structures in the inner ear shift under acceleration, helping the brain infer which way is down. Vision, pressure on the feet, joint position, and vestibular signals normally agree well enough that you rarely think about the calculation. When gravity vanishes, those cues disagree. Your eyes still see the room. Your brain knows where the floor is. But the inner ear no longer receives the familiar gravitational acceleration. The pressure from the floor disappears. Your organs no longer settle downward inside the body in the usual way. Blood no longer experiences the same hydrostatic pressure gradient from head to feet. 5 seconds is too short for the long-term physiological changes seen in spaceflight. Muscles do not atrophy. Bones do not lose mineral. The heart does not remodel. But fluid redistribution begins immediately. Standing humans normally have higher blood pressure in the legs than near the head because of gravity. Remove gravity, and that hydrostatic gradient is no longer required. Blood already inside vessels has inertia and pressure. The cardiovascular system cannot instantly adjust. For 5 seconds, the change is probably more disorienting than dangerous for most healthy people. Someone with certain medical conditions could respond differently. People connected to gravity-fed medical devices could face equipment problems. Blood, urine, stomach contents, and other body fluids do not simply leap out of place because organs contain them, but their internal pressure distributions begin changing. Then gravity returns before the nervous and cardiovascular systems have adapted. The body experiences a second abrupt transition. For many people, nausea would be almost universal, not the gentle floating often imagined in science fiction. A violent sensory contradiction followed by impact, shaking, wind, and noise. Children might recover balance faster than older adults. People already lying down would avoid some falls. Those restrained in cars or aircraft have protection from free drift but face vehicle hazards. People in water face a completely different environment because the water itself is moving. Astronauts would experience something stranger still. Suppose a crew is aboard a low Earth orbit station when Earth's gravity disappears. They are already in apparent weightlessness because station and crew are in free fall together. For them, the sudden removal of Earth's gravity produces almost no immediate sensory change inside the cabin. They are already floating. The difference appears in the orbit. The station stops curving toward Earth for 5 seconds. After gravity returns, tracking systems show the orbit has changed. From inside, the event may be less dramatic than for anyone standing on Earth, even though the spacecraft's path has recorded one of the cleanest signatures of what happened. This creates an almost surreal contrast. The people closest to what we casually call zero gravity would feel the least obvious transition when actual Earth gravity vanished. They would learn about the disaster from instruments and communication with the ground. And those communications might be chaotic. Satellite constellations require precise timing and orbit knowledge. 5 seconds of missing Earth gravity perturbs every Earth satellite according to altitude. Positioning systems would not necessarily stop instantly, but their predicted ephemerides become wrong. Receivers calculate position from precisely timed signals and expected satellite locations. Even meter-scale satellite position errors matter. Ground control would need to upload revised orbital data. Some autonomous systems could estimate discrepancies. Others would continue using old predictions until updated. Navigation errors appear at exactly the moment roads, aircraft, ships, and emergency responders most need reliable positioning. Communication satellites at high altitude remain in service more easily because their orbital perturbations are smaller and ground antennas can often continue tracking them. Low-orbit broadband constellations face larger relative orbit changes, but modern tracking can eventually reconstruct them. The event is not the end of the internet. It is another layer of confusion. The most scientifically valuable data may come from devices nobody intended as gravity detectors. Smartphones contain accelerometers and gyroscopes. Cars record inertial motion. Aircraft flight data recorders store accelerations, control inputs, pressure, and attitude. Security cameras capture loose objects drifting at different latitudes. Elevator sensors record cable tension anomalies. Ocean bottom pressure sensors record the collapse of hydrostatic balance. Weather balloons record vertical motion. Satellites provide orbital deviations. Lunar laser ranging later reveals the tiny 5-second interruption in Earth's pull on the Moon. Seismometers show the solid planet's response. The world has accidentally built a global experiment. No physicist would have been allowed to perform it. Now every instrument is part of the dataset. Within days, teams begin assembling the 5 seconds from billions of recordings. One early calculation is simple enough to fit on a classroom board. At the equator, Earth's rotation carries the surface around the axis at about 465 meters per second. The outward rotational acceleration associated with following that curved path is only about 0.034 meters per second squared, a few thousandths of ordinary gravity. If, and only if, the solid Earth were magically held rigid while a freely moving object was released from its rotating surface for 5 seconds, the surface would curve away from the object's straight inertial path by about 0.42 meters, 42 centimeters. That number becomes famous for a different reason than people first expect. It is the answer to the simplified problem. It is not a prediction of how high people actually floated during the literal event. Real videos also contain crustal displacement, structural rebound, air motion, and local elastic waves. Researchers have to subtract those signals before the small latitude dependent rotational term can even be seen. The cleaner orbital calculations survive much better. At 400 kilometers altitude, Earth gravity is still roughly 8.7 meters per second squared. Remove that inward acceleration for 5 seconds, and the difference from the normal curve trajectory is around 108 meters in the simplest short-time approximation. At the Moon, Earth's gravitational acceleration is only about 0.0027 meters per second squared. The missing curvature over 5 seconds is roughly 3 centimeters. So the same gravitational interruption leaves 3 very different signatures. A 42-centimeter rigid Earth baseline hidden inside messy surface motion. About 100 meters of missed curvature for a low-orbit satellite. A few centimeters for the Moon. And beneath the first of those numbers lies the much larger problem. The Earth itself was never rigid. This leads to a difficult question. What if we had meant a different scenario? What if only loose objects at Earth's surface became weightless for 5 seconds, while oceans, atmosphere, Earth's interior, satellites, and the Moon somehow remained gravitationally normal? That version appears often in imagination because it produces the visually satisfying scene of people and furniture floating without requiring the planet to respond. But it is not Earth losing gravity. It is a new selective force that cancels gravity for chosen objects. Under that gentler rule, the consequences would be much smaller. People initially at rest would drift only modestly because of rotation and other motion. Existing jumpers and thrown objects could travel much farther than expected. Cars would lose traction. Aircraft would become overlifted. Loose objects would fall when the effect ended. There would be accidents and injuries, but no global ocean decompression, no atmospheric hydrostatic collapse, and no solid Earth stress release. 5 seconds might then be remembered as the strangest accident in history rather than a planetary disaster. Our literal version is harsher because gravity does not know the difference between a person and an ocean. Physics does not give us a checkbox labeled loose objects only. That single clarification transforms the entire story. It also explains why the phrase zero gravity is so easy to misunderstand. NASA can create several seconds of microgravity on Earth using drop facilities. In one large drop tower, an experiment package falls in near free fall for just over 5 seconds. The duration is almost exactly our thought experiment, yet the experience is completely different. In the drop facility, gravity is still acting. The experiment and its container fall together at nearly the same acceleration, so objects inside appear weightless relative to the chamber. The surrounding Earth, atmosphere, oceans, and planet interior remain fully gravitational. Nothing is being switched off. The experiment is being allowed to fall. Reduced gravity aircraft use the same principle in a different geometry. They fly parabolic trajectories that let passengers and cabin fall together for brief intervals. Again, gravity remains strong. That is why a person can experience apparent weightlessness for seconds without an ocean rising beside them. The equivalence between free fall and weightlessness is one of the most beautiful features of gravity. Our impossible event breaks the usual situation apart and shows what free fall demonstrations normally hide. When an astronaut floats, Earth has not stopped pulling. Earth is pulling on everything together. When Earth truly stops pulling, the environment itself ceases to be in equilibrium. To continue the human side of the story, suppose the solid Earth response falls short of the most catastrophic possibilities and enough organized society survives to begin recovery. By the end of the first day, the 5 seconds have already divided history into before and after. Coastal areas assess flooding and damaged ports. Seismologists map the planet's radial and seismic oscillations. Meteorologists reconstruct pressure waves. Engineers inspect bridges, dams, towers, refineries, pipelines, elevators, and power plants. Hospitals treat fall injuries, crash trauma, exposure, and the consequences of disrupted utilities. Satellite operators rebuild orbital catalogs. Air traffic resumes cautiously where airports remain usable. Ships avoid damaged harbors and regions with continuing unusual waves. Emergency radio repeats instructions people never expected to hear. Gravity has returned and remains stable. That sentence would sound ridiculous on any other day. Now it becomes essential reassurance. Because the greatest fear is obvious. Could it happen again? No scientist can honestly promise no if the event already happened once. Known physics says it should not have happened at all. The mere existence of the event means known theory is incomplete in a way far larger than any normal anomaly. Humanity would face 2 problems at once: rebuild the world and discover whether down is still trustworthy. The psychological aftermath would be unlike the aftermath of any ordinary natural disaster. Earthquakes are terrifying, but people understand that the ground can shake. Storms are terrifying, but people understand that air can move violently. A tsunami is terrifying, but people understand that water can cross land. The 5-second event attacks a deeper expectation. Down stopped existing. For 5 seconds, every person on Earth learned that the most reliable physical condition in daily life could fail without warning. In the weeks afterward, some people would sleep on the floor rather than in beds. Others would attach furniture to walls, not because the changes would help against known physics, but because having a strap or anchor would restore a sense of control. Seatbelt use would rise dramatically. Climbers would think differently about redundant anchors. Hospitals would redesign storage so critical equipment could not drift if the impossible repeated. Aircraft manufacturers would begin asking how flight control software should respond to near-zero apparent gravity combined with atmospheric disturbance, even though no engineer could promise the event was repeatable. Architecture would change in subtle ways. Cabinets latch. Overhead objects are restrained. Elevator systems monitor tension transients differently. Laboratories install more independent inertial sensors. Nuclear and chemical facilities study what happens when hydrostatic head disappears briefly. Ports reconsider tank anchoring and crane loads. Emergency plans gain a category that would have been laughed out of every committee a month earlier. Gravity anomaly. No one knows whether that label is useful, but humanity has always been good at turning terror into checklists. The scientific response becomes even larger. General relativity has survived more than a century of increasingly precise tests. It correctly predicts gravitational lensing, time dilation, orbital precession, gravitational waves, and countless other effects. A 5-second disappearance of Earth's gravitational field while Earth's mass remains present would not be a small correction. It would demand something radically new. Physicists begin by asking whether the field truly became zero. Perhaps gravity did not vanish. Perhaps some unknown field exactly canceled its effect on ordinary matter. That possibility would be easier to imagine mathematically, because it would allow Earth's mass to remain and space-time curvature to exist while another interaction opposed the acceleration we normally attribute to gravity. But satellite and lunar data complicate the story. If every kind of matter, from people to seawater to spacecraft to the moon, experienced the same cancellation proportional to mass, the new interaction would imitate one of gravity's deepest properties, universal free fall. Then the mystery becomes almost as profound as gravity disappearing. Perhaps space-time geometry itself changed. Perhaps the relationship between mass and curvature changed for 5 seconds. Perhaps a field normally assumed constant change value. Perhaps the event was not centered on Earth at all, but Earth passed through some unknown region or wave in which gravitational coupling changed. Each idea creates new questions. Why only Earth? Why exactly 5 seconds? Why did the sun's gravitational influence remain? Did Earth's gravitational field vanish for distant observers at the same time it vanished locally? How fast did the boundary of the effect propagate? Did light passing near Earth bend differently during the interval? Did clocks at different altitudes lose the normal gravitational rate difference? Did neutrinos respond the same way as ordinary matter? Did dark matter, if present locally, respond? Did antimatter respond? The 5 seconds become the most valuable physical dataset humanity has ever possessed. Every millisecond matters. Optical fibers carrying precise time signals are analyzed. Global navigation satellite clocks are compared. Astronomical observatories search for tiny changes in the apparent positions of background stars caused by altered gravitational deflection near Earth. Gravitational wave detectors are examined for signals, though instruments designed to detect minuscule changes in distance may have saturated or responded in complicated ways to the local gravitational and seismic disturbance. Particle accelerators compare magnet records, beam trajectories, and clock timing. Deep underground neutrino detectors search their logs. Lunar laser ranging teams reconstruct the moon's position to centimeter precision. Satellite operators contribute tracking data from every altitude. The event creates a new branch of physics before the first week is over. It also creates an argument over language. Did Earth lose gravity? Or did matter stop responding to Earth gravity? Those sentences sound almost identical in everyday speech. In physics, they can describe different universes. If space-time curvature vanished, light trajectories and clock rates should change along with material motion. If an unknown force canceled gravity only for matter, light might still follow the old curved spacetime while objects did not. If inertial mass changed while gravitational mass did not, acceleration relationships could become stranger still. The 5 seconds would allow researchers to separate possibilities that had previously belonged only to theory. This is where our thought experiment has to admit its own limit. We told the story using a simple rule: Earth's gravitational pull disappears, everything else remains, then gravity returns. Real physics does not let us specify that rule without consequences for space-time, energy, momentum, and causality. Different impossible mechanisms produce different details. That is why the exact height of ocean motion cannot honestly be calculated from one sentence. It is why the exact seismic energy cannot honestly be given. It is why a precise death toll would be fiction disguised as science. But the exercise is still useful because the robust conclusions survive the ambiguity. Loose objects do not automatically accelerate upward merely because their weight disappears. But the solid Earth itself begins responding outward because the stress field that had balanced self-gravity is suddenly unbalanced. The familiar 42-centimeter rotation result is therefore only a rigid Earth baseline, not a universal human float height. Existing velocities still matter enormously. Hydrostatic pressure fields in atmosphere and ocean become unbalanced, but those fluids are coupled to a surface that is moving too. Earth's stressed interior becomes mechanically unbalanced from the first instant and receives a global outward impulse. Satellites and the Moon deviate slightly from their gravitationally curved trajectories. 5 seconds is too short to let atmosphere, ocean, Moon, or most satellites escape Earth permanently. The return of gravity does not erase the velocities acquired during the interruption. It begins the next phase, a coupled planetary oscillation. Those conclusions form the spine of the event. Now imagine a particular place rather than the whole planet. A bedroom at latitude 40 degrees north. It is 3:14 in the morning. The room is dark except for a charging phone beside the bed. A person is sleeping on their side beneath a blanket. At the instant gravity disappears, the mattress stops needing to support ordinary weight. The mattress rebounds. The bed frame unloads. The blanket no longer drapes downward in the usual way. For a brief instant, the sleeper and the room share almost the same inertial motion. Then the room stops being a passive reference frame. The foundation is attached to crust that is beginning its own mechanical response. The building can rise, flex, twist, and vibrate as loads vanish and ground motion develops. The sleeper may lose contact with the mattress, then meet it again because the mattress and floor move outward beneath them. Air in the room begins responding to the larger atmospheric pressure change. The walls delay and modify local flow. Ventilation ducts, open windows, pressure differences, and the building envelope determine how quickly outside motion communicates inward. The sleeping person wakes because the body no longer feels supported in the familiar way. For perhaps 2 seconds, there is no understanding. The blanket is drifting. The room itself is moving. The stomach receives acceleration cues that no normal experience can explain. Then gravity returns. Now the building, mattress, sleeper, phone, glass, and surrounding crust are all being pulled inward again while already carrying different velocities. The result is not a neat 20-centimeter drop. It is a collision between motions that were never designed to exist together. The phone may strike a wall or floor. The glass may shatter. The bed can slam against its frame. The building creaks as both gravity and ground stress return. Seconds later, distant alarms begin. This person might survive the entire event without a scratch. The same 5 seconds, occurring to someone on a beach, a bridge, a motorcycle, or a diving platform, could be life-changing. The contrast is important because planetary disasters are rarely uniform. Even an event affecting every square meter of Earth creates local outcomes. Gravity may be global. Risk is geographic. Time of day matters too. If the 5 seconds occurred during local night across one longitude band, more people there are lying down, restrained by beds, and enclosed in buildings. Across the opposite side of Earth, more people are commuting, working, flying, building, swimming, and operating machinery. A 5-second event at 3 a.m. Greenwich creates a different human disaster than the same event 12 hours later. Season matters. Winter snowpack on steep slopes can be destabilized by unloading and seismic motion. Frozen lakes experience different stresses than open water. Tropical cyclone season places some regions under already extreme atmospheric gradients. Monsoon rivers are in different states from dry season rivers. Tide matters less during the 5-second interval than the loss of Earth's own gravity, but it matters for how coastal waves interact with existing sea level afterward. The moon's phase changes the background tidal state. Again, no single cinematic image can represent the planet. There would be billions of stories. One of them would belong to a cargo ship in the North Atlantic. The ship is heavy with containers and moving through moderate waves when gravity vanishes. For 5 seconds, the usual relationship between weight and buoyancy collapses. The hull remains in contact with water, but water pressure begins changing. Containers locked to the deck remain connected. Poorly secured cargo can shift. Diesel engines continue turning propellers. Crew members lose footing. Gravity returns into a disturbed sea. The vessel slams into water under conditions no naval architect designed for. Containers break loose. The ship rolls. Perhaps it survives. Hours later, it faces long-period waves generated across the basin and no safe port nearby. Another story belongs to a deep underground train. The passengers feel weightlessness in a tunnel where there is nowhere far to drift. The train loses normal wheel load and traction. It continues forward from inertia. When gravity returns, wheels hit rails again. The tunnel later experiences seismic shaking, but there is no ocean surge. Emergency power may fail. The danger becomes evacuation rather than falling through space. Another belongs to a mountaineer clipped to an anchor. The rope goes slack. The climber drifts away from the face, carrying the velocity of a previous movement. 5 seconds later, gravity returns. The rope becomes a pendulum system again. The climber swings into rock. The anchor that seemed optional a minute earlier becomes the reason they survive. Another belongs to a person in a small airplane just after takeoff. Lift remains while weight disappears. The aircraft climbs sharply. The pilot pushes the nose down, but the air around the plane is changing too. Gravity returns. The runway is now below and behind, perhaps damaged by vehicles and structural effects. The flight becomes an emergency, even though the 5 seconds themselves are finished. Another belongs to a spacecraft crew. They barely feel anything. Their orbit tells the story for them. And another belongs to someone standing almost exactly at the South Pole. There is almost no rotational separation there. In the simplified rigid Earth problem, that would make the event unusually gentle. In the literal event, the advantage is much smaller. The Antarctic crust still unloads. The ice sheet loses its weight for 5 seconds while retaining internal stresses. Buildings ride the moving ground. The atmosphere still loses hydrostatic balance. Gravity returns into all of those motions. Afterward, people online still compare equatorial and polar videos, looking for the clean latitude pattern predicted by the 42-centimeter classroom calculation. They do not see it directly. The rotational signature is present, but it is mixed with ground displacement, structural motion, wind, and local geology. Physicists recover it statistically from precision instruments rather than from a simple montage of people floating higher at the equator. The result becomes a more interesting lesson than the viral version. Inertia mattered. Rotation mattered. but the reference surface itself had moved. By 1 month, rebuilding has begun in most surviving regions. Ports with minor damage reopen first. Air routes are redesigned around damaged airports. Satellite ephemerides have been corrected. Global navigation works again. Power grids are largely restored outside the worst coastal and seismic zones. Water systems are repaired. Some cities remain flooded or partially evacuated. Insurance systems face losses across nearly every category at once. Governments argue over whether the event should be treated legally as a natural disaster, an astronomical event, an unknown physical phenomenon, or something entirely new. Religious, philosophical, and cultural interpretations proliferate. The scientific answer remains frustratingly modest. We know what happened. We do not know why. That uncertainty shapes politics. Some governments build gravity shelters, low rooms with padded ceilings, anchored furniture, independent air systems, and restraints. The idea is controversial because no one knows whether a second event would last 5 seconds, 50 seconds, or never happen. Others focus on making ordinary infrastructure more tolerant of abrupt load changes. This has benefits even if gravity never fails again. Better restraint helps in earthquakes. Better emergency power helps in storms. More flexible pipe systems handle ground motion. Improved satellite autonomy handles many kinds of disruption. Fear produces useful engineering almost by accident. Scientists build instruments with one purpose: catch the next event. Gravimeters with huge dynamic range. Optical clocks linked across altitude. Laser ranging to satellites and moon. Superconducting sensors. Atomic interferometers. Ocean bottom pressure arrays. Seismic networks designed to avoid saturation. High-speed cameras pointed at reference masses in vacuum. Every continent gains facilities waiting for something that may never happen again. Children grow up practicing gravity drills in some schools. Drop flat if weight suddenly disappears. Do not jump. Grab a fixed anchor if one is nearby. Stay away from windows when gravity returns. Expect aftershocks, waves, and power failure. The drills sound absurd to the generation born after the event. Their parents do not laugh. Years pass. Gravity remains constant. No second interruption comes. The world slowly stops sleeping in harnesses. Furniture straps remain in some buildings, then become optional, then decorative reminders of a strange era. The rebuilt ports are stronger. The orbital catalogs treat the 5-second anomaly as a permanent historical discontinuity. The moon carries a tiny change in orbital state that can be traced back to one impossible interval. Sediment layers along some coasts preserve deposits from the global water disturbance. Geologists can identify the event in cores long after broken buildings are repaired. The solid Earth continues damping the oscillations excited that day. Earth's fundamental radial breathing mode has a period of roughly 20 minutes, while other normal modes span their own frequencies and damping times. Eventually, the motion becomes too small to feel, but the seismic records remain. And physics is never quite the same. The 5-second event becomes a new unit of intuition. Before it, 5 seconds meant almost nothing. A pause before answering a question. The time between a traffic light changing and the last car clearing an intersection. A breath held briefly. Afterward, people understand that 5 seconds can be long or short depending on what is moving. For a light beam, 5 seconds is enough to travel about 1.5 million kilometers. For sound in ordinary air, it is enough to travel roughly 1.5 kilometers. For sound in seawater, several kilometers. For a seismic compressional wave in crustal rock, tens of kilometers. For the moon, 5 seconds is almost nothing compared with a 27-day orbit. For a person jumping upward, 5 seconds is enough to turn an ordinary leap into a dangerous height. For Earth's rotation, 5 seconds is enough to create a tens of centimeters rigid surface baseline at the equator. even though real ground motion would be larger and more complicated. The same duration belongs to every system. The systems do not share the same clock. This is why 5 seconds matters to the planet as a coupled mechanical system. The average ocean is around 3.7 kilometers deep. A pressure disturbance moving through seawater at about 1.5 kilometers per second can traverse a depth of that order in only a few seconds. Elastic waves in rock also travel kilometers per second, while Earth's radial breathing mode operates on a timescale of many minutes. So 5 seconds is long enough to impart substantial momentum, yet short enough that the planet is nowhere near completing its response when gravity returns. If gravity vanished for only 1/10 of a second, the pressure field would begin to respond, but very little bulk motion could develop before gravity returned. At 1 second, the rigid Earth rotational baseline at the equator would still be less than 2 centimeters. More importantly, the atmosphere, ocean, and solid Earth would have only 1/5 as long to develop bulk motion before gravity returned. At 5 seconds, effects can grow rapidly wherever an unbalanced acceleration persists, while elastic and acoustic signals have time to travel kilometers through air, water, and rock. At 10 seconds, the rigid Earth rotational baseline would be around 1.7 meters rather than 42 centimeters. But by then, that small geometric effect would be even less important than the continuing expansion and stress redistribution of the planet, atmosphere, and ocean. Existing jumpers would also retain their velocities for twice as long, and pressure disturbances would propagate roughly twice as far. At 30 seconds, the scenario would become something else entirely. Atmosphere, ocean, and solid Earth would have far more time to acquire large outward velocities and separate from one another dynamically. The planet-wide radial disturbance would be much larger. Satellites would depart much farther from their expected trajectories. People and objects with modest existing velocities could travel enormous distances relative to buildings and terrain. 5 seconds sits in an uncomfortable middle ground, too short to let Earth disperse into space, long enough to launch a planet-wide mechanical response. That phrase becomes common among the scientists who study it. Long enough for the planet to notice. The ocean noticed because its pressure field lost gravitational balance while the basin beneath it was moving too. The atmosphere noticed because its hydrostatic pressure gradient lost the downward body force that had balanced it while the lower boundary itself shifted. The solid Earth noticed from the first instant because its pre-existing stress field had been balancing self-gravity, giving the whole event its dominant global radial impulse. Orbiting spacecraft noticed because gravity is what bends their paths every moment. The Moon barely noticed because its timescale and distance are much larger. Human bodies noticed because our sense of orientation is calibrated to 1G. Civilization noticed because countless systems had quietly turned gravity into an engineering assumption. There is another subtle consequence researchers would examine: time itself. In general relativity, gravity is connected not only to falling trajectories, but to the rate clocks tick. Clocks at different gravitational potentials do not run at exactly the same rate. Modern navigation systems already account for relativistic timing differences between clocks on Earth and clocks in orbit. If Earth's space-time curvature truly vanished for 5 seconds, rather than being canceled by some unknown force acting on matter, the gravitational contribution to those clock rate differences would also change during the interval. The effect across only 5 seconds would be tiny. Modern optical clocks, however, can measure astonishingly small differences in gravitational potential. After the event, timing records from laboratories at different altitudes and from satellites could help answer the most important theoretical question: did gravity disappear from space-time, or did matter merely stop falling as though it had? A clock becomes a witness. So does light. Earth bends passing light by an extremely small amount. If the space-time curvature associated with Earth vanished, light passing near the planet during those 5 seconds would follow a slightly different path than expected. Detecting such a tiny, transient change would be extraordinarily difficult, but astronomers would search archival images and radio signals for it. The mystery becomes less about falling objects and more about the structure of reality. Suppose the clocks changed exactly as general relativity would predict for the disappearance of Earth's curvature. Then somehow mass stopped sourcing gravity. Suppose the clocks did not change, but matter and the moon still stopped accelerating toward Earth. Then an unknown force imitated anti-gravity with extraordinary universality. Either answer would be revolutionary, and either answer would make the 5-second catastrophe scientifically priceless. That creates an uncomfortable moral contrast. The same event that killed people, damaged coasts, and frightened a planet would be the greatest experimental clue in the history of physics. Researchers would study it for generations. No one would wish for a second occurrence. Everyone would want more data. This tension appears whenever nature performs experiments humans could never ethically create. Earthquakes reveal the planet's interior while destroying cities. Supernovae reveal stellar physics while annihilating worlds that may once have existed nearby. Cosmic collisions teach us how matter behaves at energies no laboratory can reach. Our impossible gravity failure would be the most extreme example. The universe gives 5 seconds of data at an unacceptable price. Decades later, the people who were children during the event become physicists, engineers, oceanographers, and seismologists partly because they remember floating. One of them had been 6 years old in an apartment near the equator. She remembers waking from an afternoon nap and seeing a stuffed animal drift from the bed. She remembers the mattress suddenly feeling absent beneath her. Then she remembers the room itself moving. She remembers the impact when ordinary weight returned, the windows rattling, and her parents carrying her down dark stairs because the elevators had stopped. As an adult, she works at a laboratory containing a polished metal sphere suspended inside a vacuum chamber. The sphere is watched by lasers and atomic clocks. It is not an anti-gravity machine. It is a trap for information. If Earth's gravity ever changes again, the sphere's motion will be measured thousands of times per second. The laboratory has operated for 23 years. Nothing has happened. Gravity has remained boring. That is exactly what everyone hoped for. Yet the instruments stay on. Around the world, similar observatories remain awake. Some are underground to reduce vibration. Some sit on isolated plateaus. Some are in orbit. Some use atom interferometers, watching quantum matter respond to acceleration. Some compare clocks separated vertically by towers or mountains. Some fire lasers at reflectors on the moon. Some monitor pressure on the seafloor. A global network waits for one impossible signal. It becomes known informally as the Down Network. Not because that is its official name, because everyone understands what it is waiting for. The day Down fails again. It never does. A century passes. The 5 seconds move from living memory into recorded history. Buildings carry small plaques showing which structures survived the gravity interruption. Coastal memorials mark communities lost to the water disturbances that followed. Museums display ordinary objects recovered from rooms where cameras captured their trajectories. One exhibit holds a ceramic cup. It is not famous because it broke. It did not. The cup had been sitting on a kitchen counter near the equator. A high-speed home camera captured its motion. For the first instant, the cup does almost what inertia says it should. Then the counter beneath it begins moving with the building. The room flexes. Air shifts. The cup and the surface that had supported it acquire different motions. They separate, meet again, and slide apart before gravity returns and the entire room is loaded once more. The video becomes a standard physics lesson precisely because it refuses to show one clean answer. Children expect the cup to blast toward the ceiling. It does not. They also expect the counter to remain a fixed reference. It does not. Teachers pause the recording at the first frame. What upward force appeared on the cup when gravity vanished? None, a student eventually says. Then why does the distance between cup and counter change? Because the counter is moving too. Exactly. Removing gravity did not create a mysterious upward force on the cup. It removed the force that had helped hold the entire planet in its previous mechanical state. Then the teacher shows videos of air movement, ocean pressure records, and seismic signals. The lesson changes. What was pushing upward before gravity disappeared? Now the answer is more complicated. Pressure, elastic stress, buoyancy, aerodynamic lift, normal forces, tension. Structures and fluids were already full of forces pointing in many directions. Gravity had been part of the balance, not the only actor on the stage. This may be the deepest conceptual lesson of the event. We often imagine gravity as an isolated downward arrow, a force that pulls things to the floor. But on Earth, gravity is woven into equilibria. A table pushes upward because gravity pulls a cup down. Atmospheric pressure changes with height because gravity pulls air downward. Ocean pressure changes with depth because gravity pulls water downward. Buoyancy exists because pressure is greater below an object than above it in a gravitational field. Mountains are shaped by the competition between rock strength and gravity. River valleys exist because water moves downhill. Sediments settle because particles fall. Trees grow structures that resist their own weight. Animals evolved skeletons and muscles within 1G. Human architecture is a conversation with gravity written in stone, steel, concrete, cable, and wood. Remove gravity for 5 seconds, and the conversation does not stop. One speaker suddenly goes silent. Everything else responds. The return is the answer shouted back. By the time those future students leave the museum, gravity has been reliable for more than 100 years. The event is extraordinary history. The fear has softened, but scientists still cannot explain why it happened. Perhaps that is fitting. Gravity itself was once described as a force acting across empty space. Then Einstein reframed it as geometry. Modern physics can describe gravity with extraordinary precision on large scales, yet a complete quantum description remains one of the deepest unfinished problems in fundamental physics. We know how planets move. We can navigate spacecraft between worlds. We can detect ripples in space-time from black holes billions of light years away. We can correct satellite clocks for relativity so phones can locate themselves on Earth. And still, at the deepest level, gravity refuses to fit comfortably beside the quantum description of the other fundamental interactions. Our 5-second event would not solve that problem. It would make it impossible to ignore. There is a temptation, near the end of a thought experiment like this, to turn the disaster into a message that gravity is our friend. Physics is less sentimental than that. Gravity causes falling injuries. It drives landslides. It helps collapse stars. It pulls asteroids into impacts. It makes launching anything into space difficult. It contributes to enormous pressures inside planets and stars. Gravity is not kind. It is consistent. And consistency is what life has adapted to. Every organism on Earth's surface is the product of ancestry lived under nearly the same gravitational field. Bones remodel under load. Trees thicken in response to stress. Roots follow signals influenced by orientation. Fish regulate buoyancy. Birds generate lift against weight. Human brains build a map of space in which dropped objects fall. The comfort of gravity comes not from gentleness, but from reliability. 5 seconds without it would reveal how much of a world can be built around one dependable condition. There is one last place where gravity has been doing invisible work: underground water. Aquifers are not underground lakes in giant empty caves. Much groundwater occupies pores and fractures in rock and sediment, moving under combinations of pressure and gravity. Wells work because hydraulic head gives water a tendency to move from one state of potential toward another. Springs emerge where geology and pressure allow groundwater to reach the surface. For 5 seconds, the gravitational part of that system vanishes. Water already flowing through pores keeps its momentum. Pressure gradients remain temporarily. In confined aquifers, water under pressure may continue moving even without gravity. In unconfined systems, the relationship that defines a water table begins to lose meaning because there is no longer a preferred downward direction. 5 seconds is too short to drain an aquifer or rearrange regional groundwater. Rock pores are small and groundwater velocities are usually slow, but wells and pressure sensors would record abrupt transients. Water columns in deep wells could oscillate after gravity returned, much as wells can respond to distant earthquakes, except the forcing here would be global and fundamentally different. Caves would produce their own strange recordings. A stalactite grows because mineral-rich water follows gravity to a low point, forms a droplet, and leaves a tiny deposit when chemistry allows. During 5 seconds without gravity, droplets hanging from cave ceilings no longer have the same reason to detach downward. Some remain attached by surface tension. Others already falling continue along their existing paths. Underground streams lose the slope-driven component of flow. Then gravity returns, and millions of small water movements resume at once. None of this matters much to immediate casualties. It matters enormously to scientists trying to reconstruct what the event touched. The answer becomes almost everything. Groundwater, glaciers, ice sheets, sediment, lava, the atmosphere, the ocean, the solid planet. Even glaciers are not rigid blocks simply sitting on rock. Their enormous weight contributes to pressure at the base. Gravity drives ice to deform and flow from thicker, higher regions toward lower ones. Remove gravity for 5 seconds and that driving stress disappears. The ice does not race uphill. Its existing deformation and momentum barely have time to change. But basal pressure conditions and crevasse stresses experience a sudden unload and reload. At the margins of ice sheets, cliffs of ice and floating shells respond differently depending on whether they are grounded or already supported by seawater. Because seawater itself is undergoing a pressure crisis, the usual distinction between grounded ice and floating ice becomes temporarily unstable. Again, most of the long-term ice sheet survives. The event is too short to melt it, break it all apart, or move it far. But the 5 seconds leaves stress waves and fractures that can continue evolving afterward. Earth's shape adds another layer. Our planet is not a perfect sphere. Rotation makes it slightly wider at the equator than from pole to pole. Self-gravity normally works against the outward effect of rotation and helps maintain an equilibrium figure. When self-gravity disappears, the rotational tendency does not. For 5 seconds, matter at lower latitudes has an additional reason to continue outward relative to the axis. The planet cannot reshape itself into a dramatically different figure in 5 seconds. Rock and mantle have too much inertia and the distances are too large. But the stress change is not perfectly spherical. Latitude matters inside Earth as well as on its surface. When gravity returns, the tiny shape perturbations and larger pressure-driven motions are folded into the global oscillation. In the aftermath, geodesists would compare the exact positions of observatories before and after the event. Modern techniques can measure crustal movement with extraordinary precision. They would ask whether continents shifted by millimeters, centimeters, or more. They would map permanent deformation near faults. They would compare Earth's rotation rate and orientation before and after the 5 seconds. Could the length of the day change? Slightly, perhaps. If mass is redistributed within Earth, the planet's moment of inertia changes. Conservation of angular momentum then changes rotation rate, much as a spinning skater changes speed by moving mass inward or outward. Real earthquakes can change Earth's rotation by tiny amounts because they redistribute mass. Our global event could also do so. The exact size would depend on the internal response, which is one of the least certain parts of the scenario. But after gravity returned, atomic clocks and astronomical measurements might find that the day was no longer exactly the length it had been before. Not by minutes. Perhaps by amounts far too small for a person to feel, yet large enough for precision geodesy to detect. The location of Earth's rotation axis could shift slightly as well. This is another reason the event cannot honestly end when the 5th second ends. A force can return instantly. Equilibrium cannot. The ocean needs time to settle. The atmosphere needs time to settle. The solid Earth needs time to settle. Human systems need time to settle, and some records never quite return to their previous values. A satellite enters a slightly altered orbit. A fault slips. A coastline receives a new sediment layer. A bridge is permanently bent. A person's memory keeps 5 impossible seconds. That is what makes the thought experiment larger than the number 5 suggests. The interruption is short. Its aftermath has no fixed duration. Some familiar forces, meanwhile, barely care that gravity is gone. A compass still points according to Earth's magnetic field. The magnetic field is generated by motions in the electrically conducting outer core, and 5 seconds without gravity would not make that field vanish on command. The core's mechanical state begins changing, but electromagnetic fields do not switch off simply because gravitational acceleration does. Magnets still stick to refrigerators. Electric motors still turn. Chemical reactions still proceed. A battery still produces voltage. A radio can still transmit. The sun still shines. Photosynthesis does not stop because gravity is absent for 5 seconds. Light bulbs remain bright until power systems trip for other reasons. Fire becomes strange, but not impossible. Combustion chemistry continues. What changes is convection. On Earth, hot combustion gases normally become buoyant relative to cooler surrounding air and rise, helping produce the familiar teardrop shape of a candle flame. In weightlessness, that buoyancy-driven flow disappears and flames can become more rounded, supplied by slower diffusion and whatever forced air motion exists. Our event lasts too briefly for every fire on Earth to settle into a perfect microgravity flame. The atmosphere itself is accelerating and turbulent, so many fires experience rapidly changing airflow instead. But the familiar upward stretch of flame is another ordinary phenomenon whose geometry had been quietly depending on gravity all along. When gravity returns, convection returns too, inside an atmosphere that is no longer calm. Fires damaged by broken fuel lines or electrical faults may therefore become part of the secondary emergency. This contrast helps define the boundary of the thought experiment. Gravity disappearing does not turn physics off. It reveals which parts of the world had been using gravity without announcing it. The things that keep working are almost as informative as the things that fail. Now return to the instant before the event. The woman is still in the kitchen holding her coffee. The child is still on the staircase. The goalkeeper is still leaning forward. The train is still entering the station. The cargo ship is still moving through the North Atlantic. The astronaut is still floating in orbit, already falling around Earth without feeling weight. The Pacific is still pressing against its seafloor. The atmosphere is still arranged in layers of pressure and density. The mantle is still carrying stresses accumulated over geological time. Every satellite is still curving around the planet exactly as predicted. The moon is still falling around Earth in its long orbit. Nothing knows that the impossible is 1 second away. Then gravity disappears. Not with a flash. Not with a sound. There is no gravitational thunder. There is simply less force than there should be. The coffee stops weighing on the hand. The child loses reliable contact with the stare. The goalkeeper continues into a motion that no longer has the expected down. The train unloads against its rails. The ship enters an ocean whose pressure balance has broken. The astronaut notices almost nothing. 1 second, air begins to respond. Structures rebound. Loose objects drift. 2 seconds. Cars discover that friction was never just a property of rubber and asphalt. It needed them pressed together. Aircraft discover that lift was designed to oppose a force that is temporarily gone. 3 seconds. Pressure information races through water. The solid Earth begins responding to the absence of its own inward pull. For seconds, people have time to understand only that the world is wrong. 5 seconds. Gravity returns. Objects fall. Air reverses. Water is recaptured. Rock is reloaded. Orbits curve again. The moon continues. The planet remains a planet. What happens to civilization is harder to promise. If the solid Earth motion falls toward the gentler end of plausible responses to our impossible rule, large parts of humanity may survive amid an unprecedented global disaster. If the mechanical rebound is far more violent, the consequences could be vastly worse. Our premise is not precise enough to calculate that honestly, and the 5 seconds become evidence that the most ordinary forces are often the ones supporting the greatest amount of hidden structure. That is the answer to the question. If Earth truly lost its own gravity for 5 seconds, the world would not gently float and then settle back exactly as before. Loose people and objects would not accelerate upward merely because a downward force vanished. But that does not mean they would float peacefully a fixed distance above an unmoving floor. The floor is part of Earth, and Earth itself had been held in its present stressed configuration partly by self-gravity. In the literal version of the scenario, that planetary response becomes one of the dominant uncertainties. 5 seconds would not strip away the atmosphere. It would not fling the moon into space. It would not stop Earth's orbit around the sun. It would not automatically make every object fly away. But it would be long enough to disturb atmosphere, ocean, and solid Earth on a global scale, and long enough for the return of gravity to turn those disturbances into waves, impacts, shaking, and cascading failures. Whether civilization recovers quickly, slowly, or only in fragments depends on a solid Earth response that our impossible premise does not specify well enough to calculate. Whatever survives would never think about down in quite the same way again. And now the imagined 5 seconds are over. Gravity has not disappeared. The room around you is behaving in the familiar way it always has. A glass placed on a table stays there. A blanket settles downward. Air remains quietly layered above the surface of the Earth. Oceans remain gathered in their basins. The moon continues along the orbit it has followed for billions of years. If you are lying in bed, the mattress is pushing upward against your weight while Earth pulls gently downward. Those two forces are close enough to balance that you remain still without needing to think about either of them. The stillness feels simple. It is not simple at all. Beneath it is a planet turning through space, an atmosphere held in a pressure balance, oceans shaped by gravity, rock compressed deep below, and a gravitational field extending far beyond the moon. All of it is happening without asking for your attention. The thought experiment can stay where it belongs now, inside imagination. There is no known switch that can turn Earth's gravity off for 5 seconds. No hidden countdown is running. Nothing in ordinary physics suggests the ground can simply stop pulling in the way we imagined. So the 5 seconds can fade. The cup can remain on the table. The ocean can remain beyond the shore. The moon can continue falling around Earth, never reaching the ground. And the familiar weight of your own body can become part of the quiet rather than something to notice. Gravity has been shaping Earth for billions of years before this night, and will continue after it. For all the strange physics we can imagine, this moment requires no correction. Down is still down. The planet is still turning. The air is still here. And the world, for now, is exactly where gravity keeps it. Let the questions become smaller now. Not what happens to the oceans. Not what happens to satellites. Not what happens inside the mantle. Only the ordinary feeling of being supported by whatever is beneath you. The strange 5-second world has closed. There is nothing more to calculate tonight. Nothing is floating away. Nothing needs to be held down. The same gravity that gives falling its danger also gives stillness its shape. And in that familiar stillness, the day can finally become quiet. Good night.